Thank you for joining us in our last lecture series of the Quantum Winter event. This is Abhishek Chopra, the CEO and founder of BosonQ Sci, and today we are joined by a very well-known person from the quantum computing arena, Jin-Peng Liu. He's a PhD student at University of Maryland. So before moving on with the presentation, I would request the organizers to briefly mention about uh, their organization, and then we can start on with our presentation. So from International Society for Computational Fluid Dynamics, we have Jesus. So Jesus, you can go ahead and introduce yourself and ISCFD.
Thank you, Abhishek. As Abhishek kindly introduced me, my name is Jesus Miguel. I'm a board member of the ISCFD, the International Society for Computational Fluid Dynamics. And in our organization, we are focused on spreading the knowledge of CFD by organizing live events such as webinars right now due to the current pandemic. And in the past, we used to also focus on organizing face-to-face events. So I would like to take the pleasure to thank Abhishek and his team for collaborating with us again in this very interesting webinar. And thank you.
Thank you, Jesus. Thank you for that lovely introduction. So our other organizers is Quantum Computing India, and together the three of the organizations came together for making this event possible. And this is one of the first event that has been organized in quantum computing with application in multiphysics simulation. So as seen from other talks, we dwelled into various aspects of multiphysics simulation, and today we will be talking about the the most important or the central part of all these multiphysics simulation, like the partial differential equation, and how can we solve that using quantum computing. So without wasting any more time, I would ask Jin-Peng Liu to take over and start with this presentation. First of all, welcome Jin-Peng, and thank you for accepting to talk to us today and share your views on this exciting topic.
Thanks. So I think we can begin now. So I'm Jin-Peng. Today I'd like to briefly talk about high precision quantum algorithms for partial differential equations. It's a joint work with Andrew Charles, who is my advisor, and with Aaron Ostrander. Here is our recent paper and with the archive number. And first of all, I'd like to briefly introduce some basic concepts about quantum computing and why we are care about how to solve partial differential equations by quantum computers. Then I would like to introduce the high precision quantum algorithms for PDEs. Basically speaking, quantum computing is to use quantum mechanics phenomena such as superposition and entanglement to perform computation, and we expect that it can be more efficient than classical computation. There are a few different approaches to build quantum computers, such as optics, trapped ions, quantum dots, and superconducting circuits. Several research groups in this world are making strong efforts to build more and more powerful quantum computers. They are IBM, IonQ, Google, et al. But basically speaking, and as a prime mathematician, I would like to mainly focus on how to design and develop proper quantum algorithms running on powerful quantum computers. So today we may more focus on the algorithm size. So for all the quantum algorithms, in my mind, we can have two types of quantum algorithms. The first one I would like to call the provable quantum algorithms, including Hamiltonian simulation, quantum Fourier transform, and many other algorithms. For these kinds of algorithms, we do have certain upper and lower bounds and certain speedups over classical computation. But perhaps in this approach, and it might be hard to be implemented in near-term device. Another class is about heuristic quantum algorithms, including adiabatic quantum computation and quantum approximate optimization algorithms and et al. For these kinds, they are available for near-term quantum device, but they are usually lack of theoretical guarantees. Basically, I'm mainly focused on the first one just because we perhaps more focusing on the long-term study and we are care about what's the certain quantum speed up we can achieve, and we want to find some problem that is extremely hard to be simulated in classical computers, but it might be potential applications for quantum computers. And for the quantum computing, I'm mainly focus on quantum scientific computation, and scientific computation is a word from a premise. Basically, we expect quantum computers can be used to dramatically speed up some numerical linear algebra problems by encoding the solution of a system in a Hilbert space. For the problem models, we are caring about the following problems, including Schrödinger equation, linear system, and ordinary or partial differential equations. And specifically, we are caring about what's the behavior about the dimension and the precision. The first fundamental quantum algorithms for such kinds of problem is to efficiently simulate Schrödinger equation by Hamiltonian simulation. I think it's one of the most important quantum algorithms. So the problem model is formed as the equation 1. Equation 1 is a Schrödinger equation written in a Hamiltonian form with the Hamiltonian edge. And our goal is to construct algorithms like the equation 2, which can be used to approximate the equation 1 efficiently. So here is the problem description. So given a sparse or local Hamiltonian and evolution time and initial state, our goal is to produce the final state within error tolerance. And the first Hamiltonian simulation algorithm is proposed by Seth Lloyd in 1996 based on product formulas. He successfully developed a quantum algorithm with the complexity polylaw dependence with the dimension n and polydependent with the precision 1 over epsilon. So for the dimension is true just because for any classical simulation results and they suffer from a poly scale with a dimension n. But here in quantum computers, we can achieve polylaw dependence of dimension n. But the dependence of the precision is far from ideal because it's only poly 1 over epsilon. It's sometimes pretty slow. But this result is improved by some papers from 2015 and 16. They apply LCO, which means linear combination of unitaries or quantum signal processing to improve the dependence of precision from poly of 1 over epsilon to the polylog 1 over epsilon. And so here, we can find several applications of such kinds of representative quantum algorithms. Of course, the direct applications is to simulate quantum many-body physics in many settings. Also, it can be used to implement wide-range quantum algorithms. And I think the most important thing is the second fundamental algorithms I'd like to introduce in here is to use Hamiltonian simulation to implement quantum linear system algorithms. So here is our second model. We can look at the equation 3. I think most of us will be pretty familiar with these linear systems. Given a sparse or some condition like we call it Encoding, and by a matrix A, and given a quantum state representing the inhomogeneous B, and our goal here is to propose a normalized state S, which is proportional to the inverse or a pseudo-inverse of these linear systems within an error tolerance. So similarly, and in the development of quantum algorithm, the first algorithm which is well known as HHL, proposed in 2008, that can achieve exponential speed up for the dimension, which is poly log 1 of n. But at that time, the dependence of precision of HHL is not good. So recently, it can be further reduced to polylog 1 of epsilon. And so for here, I think compared to the previous algorithm for simulating Schrodinger equation, I think people will understand how important given a linear system algorithm. And so it can be used to solve various data science problems such as optimization and machine learning. Also, in the physical science, I think the most important application of this algorithm is to use to simulate many kinds of differential equations. So here we are moving on to our third fundamental problems. From Schrodinger equation to linear system to ordinary differential equations. So here our problem model is equation 4. Is a general linear ODE problem with boundary conditions. Of course, if beta is equal to 0, it is reduced to an initial condition. And we are given some assumption for this linear system, like the A should be the time-dependent matrix A of t can be diagonalized, and all the real parts of the eigenvalues of A are not positive. And our goal is to, sorry. So perhaps let's continue, and any question can be asked later. Yeah. Then let's here our goal is to output normalized states and with some time S of t, which is proportional to the solution of the ODE within error tolerance. Here also there are several algorithms are developed, and they are also follow the basic procedure. First, reduce the dimension dependence from poly n to polylog n. And second, reduce the dependence of precision from poly 1 of epsilon to polylog 1 of epsilon. So they are pretty similar. So here, basically, we can find a very interesting observation is simulating ODEs matches the results of Hamiltonian simulation. So which means Schrodinger equation in a discretized form is a special case of ODEs, but we can still solve general ordinary differential equations well by quantum computers. Also notice that in the following paper, the CL19 is our paper last year to propose a quantum spectral method for simulating ordinary differential equations. Wait, okay. Yes, so after the ordinary differential equations and now we are moving on to partial differential equations. And so why solving PDEs is important and why it's harder than ordinary differential equations? I think there are several reasons from theoretical and application perspective. For theories, one thing is we are caring about how powerful quantum mechanics can be used to simulate complex worlds, including thermodynamics, electrodynamics, fluid dynamics, et al. So for those kinds of complicated macro physical phenomena is different from quantum mechanics. So which we imagine using one mechanics to simulate other kinds of mechanics will be hard. Also, we have various problem settings in PDEs. we can solve initial boundary value problems, we can solve scattering problems, and we can solve inverse problem, controls problems at all. So for those kinds of competitive settings, it's hard to develop a general algorithm to solve everyone here. And for the application side, while solving PDE is important for applications, one reason is PDE is widely used in aeronautics, plasma, finance, et al. So if we can develop efficient quantum algorithms for solving PDEs, and if it can be successfully run, and it can be a killer app in the future. And actually, recently, Airbus proposed a quantum challenge to ask people to propose some plans to use quantum computers to solve problems from aeronautics. And NASA also has a quantum AI lab aiming to develop quantum algorithms specifically. Also, because PDE is widely used to as a basic tool to characterize many phenomena and many properties of the system. So algorithms for solving PDEs can be used to be a subroutine for any other algorithms. But also here I'd like to point out that basically solving some high-dimensional and hard PDEs will be hard to find near-term applications just because we need more powerful quantum computers to implement some algorithms in a large scale. But perhaps we can try to find some toy model to solve in near term. And that will be a very interesting problem here. So, okay, so now we are moving on to high precision quantum algorithms for PDEs. So here I'd like to give a general mathematical definition of linear PDEs. So you can see as the equation 5, we are given a very general form of the PDEs. It's a set of the PDEs and of the scalar function u, but here we assume S is in a d-dimensional domain D, and here we assume the capital D is a hyperfield. And we are given some assumptions for these equations, like we assume it's a second order elliptic PDEs, and it satisfies a global straight diagonal dominance condition. The special case is Boson equations, but it can be generalized to the general elliptic equations. And we assume that this weight solution of these elliptic equations such that we can guarantee after solving a numerical solution is a true approximation for the exact solution. We also assume some assumption for the oracles, like how to efficiently prepare the coefficients and the input states and for this problem. And the goal here is a basic description. Because u of x, u is a scalar function, so our goal is to output a normalized vector u of kappa, which is proportional to the exact solution u kappa, where kappa is a set of interpolation nodes. So basically, we try to propose a discretized distribution of the solution on a given interpolation nodes. And so for these kinds of problems, there are many kinds of classical algorithms are developing to solve these problems. And specifically, we care about problems with large dimensions. For these problems arising in interacting particles, or it can be used to approximate stochastic process. And the basic model of that is Boson equation as well as elliptic equations. Because we care about problems with extremely large dimensions, so for classical algorithms, they will suffer from a curse of dimensionality, which means if you look at the complexity of those algorithms, so even for the standard finite difference method, finite element method, and finite volume method, and spectral methods, and the complexity dependence scales exponentially with dimension d. So even if we perform some advanced sparse grading methods, and the complexity still depends on some constant truly d. So here, because d is a large dimension, so classical algorithms rapidly become infeasible. Quantum algorithms are expected to speed up the problems for the dimension. So basically, we expect we can achieve a polydependence of d by quantum algorithms. So in the past, there have been developed many quantum algorithms for different PDEs, like Poisson equation, Maxwell equation, wave equation, linear hyperbolic equations, and heat equation. So for these problems, you can see I try to summarize the complexity results of previous quantum algorithms. But basically, you can see these algorithms are not the dependence of the dimension is good, but the dependence of the precision is not good enough because it can only achieve a polydependence of 1 over epsilon. Precision is so for these results, and the main reason is not for it can only achieve a polydependence of 1 over actually we can perform high precision. So for these results, and the main reason is not for it can only achieve a polydependence of 1 over actually we can perform high precision. So for these results, and the given main reason is not for it can only achieve a polydependence of 1 over actually we can perform high precision. For these results, even reason is not for only achieve a polydependence of 1 actually we can polydependence for this results even reason is not for only achieve a polydependence of 1 actually we can polydependence for this results even reason is not for only achieve a polydependence of 1 actually we can polydependence for this results even reason is not for only achieve a polydependence of 1 actually we can polydependence for this results even reason is not for only achieve a polydependence actually we can polydependence for this results even reason is not for only achieve a polydependence for all actually we can polydependence for this results even reason is not for only achieve a polydependence for all actually we can polydependence for this results even reason is not for only achieve a polydependence actually we can polydependence for this results even reason is not for only achieve a polydependence actually we can polydependence of K and N. Then try to which is satisfied the error of K and N control. Then we try to which is satisfied K and N which is K is equal to N to the B. Then we try to optimize the horizontal K and N, which is can to choose to guarantee the K and N still as only not optimize our horizontal N. So that's a very simple basic idea. So to use that, for example, when we consider discretization for boson solution, so that's the first step we need to perform discretize, for example, when we consider discretization solution, so then we consider what's the discretized boson solution. So then we consider what's the discretized boson solution. We have d-dimensional tensor sum, and the solution U of S is smooth, which can be guaranteed by elliptic PDEs, and then the error will decrease with the scaling epsilon to the epsilon scale as 1 over n to the k. So it's actually a n plus 1 to the d dimensional linear system with a certain sparsity n times d. You can see the global dimension of this linear system is pretty large, but the sparsity is basically fine. So what's the expression of the equation 12? It has been given by the previous literatures, and here the equation 13 is the form of a 2n order string for the second order derivatives. So here and S is 2n times 2n matrix with expression like this. Sij is equal to 1 if and only if the absolute value of I minus j is equal to 1. And for other entries are 0. And then what's the coefficients? And in the equation 14 is the exact expression for the coefficient Rj. So basically speaking, for these kinds of discretization scheme, it can be ensured that the error scales as 1 over n to the k. Actually, this discretization has been used in previous literatures of quantum computing, like the quantum simulation of many-body physics, and also the paper for fast quantum packages. We have already known the sting, and we just try to plug in the sting and back to the boson equation. We just try to, we have already get a sparse linear system in the equation 11. And then we are able to solve it efficiently by quantum linear system algorithms. Also, I'd like to give some concrete implementations here about the boundary conditions. I try to give a fourth order string as an example, just because I think many of us will be familiar with second order string. The 3 points pencil like 1 minus 2 1 is too boring, so let's consider fourth order string. And you can see the 5 points pencil of a fourth order string still as the third line of the matrix in the equation 15, the 1 of 12 minus 2 of 3, just this line. So near the so within the boundary, we just write down the discretization form by this 5 point pencil, and but near the boundary, if we consider de-Hurley boundary conditions, and we just directly modify the matrix by taking a principal submatrix, which means we directly ruling out the first 2 lines and for first 2 rows and first 2 columns, and just only keep all the nodes within the boundary. Is fair enough for de-Hurley boundary condition. And then what about the Newman boundary conditions? Now we need to adjust the numbers nearby the the boundary. Like even for the 5-point pencils of the first order string, and then you can see the basic rule is that we need to add the values of first and second columns onto the third column. And then, of course, we then delete the first two columns and first two rows to reduce it to all the nodes within the boundaries. It's some very standard procedures from the classical computation. So here is the basic, some simple example to encode the Poisson equations for on the boundary. And for within a boundary, we directly implement these results. And for the d-dimensional problems, we just try to use the previous equations 11 using the tensor sum to encode a very large linear system. Then it can be solved efficiently by quantum linear system algorithms. Then I would like to also introduce another approach we call the quantum spectral methods. It's inspired by classical multi-dimensional pseudo-spectral methods. The basic idea for the spectral method is to find a global approximation instead of local approximation. We directly try to approximate the global functions over the domain instead of look at the approximations on nearby points. So for the equation 17, we just use this finite truncated expansion of some basis functions to approximate the exact solutions. And then here we can see because it's a d-dimensional solution, and we need to use sum of tensor products of some base functions. And here we can see the u of kappa, the interpolation is located in the base function. And then we also have some unknown coefficient ck, where c is n+1 to the d vectors. So our goal is actually try to transform the problem of solving u to solving the coefficient c. It's pretty simple to directly look at how to solve the coefficients. So after we have obtained this representation of equation 17, we just try to plug in these expressions into the PDEs to get the equation 18. So you can see, and basically speaking, we just directly take the truncated solution into the differential equations, and we assume this system and is equal to the inhomogeneous over the interpolation nodes, and so this approximation has the n+1 to the d coefficients unknown, and n+1 to the d equations from the n+1 to the d interpolation. So the number of equations and the number of unknown coefficients are equal. Then some remarks from the classical theories of spectral method. If the solution is smooth, which is guaranteed by the results of the elliptic equations, and the error decreases exponentially with the which is at epsilon scale as 1 over n to the n. However, even if we have a very good exponential decrease property in here, we actually obtain a n+1 to the d dimensional no-sparse linear system. So now our goal should try to decompose such kinds of no-sparse matrix structure by some specific transformation based on the structure of base functions. So what is our base function we choose? So for periodic boundary conditions, as usual, we can choose Fourier base functions. For non-periodic boundary conditions, we need to consider Chebyshev polynomial of the first time as the base functions. Also, for quadrature nodes, For periodic boundary conditions, we consider uniform grain nodes. And for the non-periodic boundary conditions, we should consider the Chebyshev, Gauss, Lobato projection nodes. So now we need to consider what's the differential matrix when we plug in the truncated solution into the differential equations. Perhaps we can go back to look at the equation 18 here, and because we have already plugged in the equation 18 to equation 17 to equation 18, so you can see when we take the derivatives of u of k by l, actually we are taking derivatives to the base function and then plotting the interpolation nodes. So we don't, because ck is constant, and so we just take the differential is to about the tensor form of the base functions. So here is the form expressed in the equation 21. You can see the good news is when we take the derivatives of one coordinates, and then we can find, and we just only need to change perform differential equations on the one coordinate, rj, the j coordinate. For the rest, d minus 1 coordinates, the matrix structure is unchanged. And what is the differential equations? And for Fourier-based function, we can have a diagonal matrix as the form in equation 22. And for the Chebyshev polynomial, it's much complicated because it has it's an upper triangular matrix. It's a non-symmetric matrix. And then for this, and because we need to consider the base functions, and for example, if we consider the Fourier basis, and we need to find a discretized form, and which can be efficiently transformed by quantum computers. So here we actually developed a very similar version of QFT of quantum Fourier transform. We call it quantum shift Fourier transform. It's just try to change the phase factors within a Fourier function. Also, we consider another kinds of the transform we call it quantum cosine transform. The reason is this cosine kj or j pi comes from the interpolation nodes in the equation 20 like this. So for the d-dimensional tensor products, we need to consider this transform in the equation 25. Also, just notice that even if the global the dimension is n plus 1 to the d, and we prove those kinds of transformation can be both efficiently performed with the complexity linear with d and log dependent with n, which are both exponential speed up over n and d compared to the classical of fast Fourier transform and fast cosine transform. So finally, after those previous ingredients, now we can consider how to solve the problems. Here I try to consider a two-dimensional Boson equation as an example, just because 1D is too trivial, and also we consider non-periodic boundaries because it's complicated than periodic boundary conditions. So here is the equation like the Laplacian u is equal to f, and in a 2D hypercube, and we choose the truncation number n is equal to 3. Now we assume C and F are Chebyshev coefficients of U and F. And notice that the dimension is 2, so we have C K1, K2 and F K1, K2. And because we choose the truncation number is n is 3, so K1, K2 range from 0 to 3. So we actually have 4 times 4 6-dimensional vectors for C and F. Now, because we need to solve the coefficients after the transformation, so the linear system can be written as this form, and here we can see after the transformation by the Cn, and we have already obtained sparse linear systems. And the form can be written as the equation 26. Here we can see what happens to this is because the first of all we should consider the sum of tensor product d of times I and I of times u. Then for this form, the differential matrix like this 2r over the sigma k, which is actually for this n is equal to 3 case, is reduced to the 4 and 24 two numbers. So it looks pretty sparse and actually is not a full-range system. The reason is for here, for non-periodic boundary conditions, we need to carefully deal with the boundary conditions. And let's consider here is the two-dimensional hypercube. It's a square, so we have 4 lines, 4 sides from east, west, north, and south. So we need to consider the 4 boundaries and US1, 1, US1 minus 1, U1 as 2, and U minus 1 as 2. And we use the Gn, Gh, Ge, and Gw representing the coefficients of those 4 boundary conditions. Then for this is actually the first 1D functions. So we can perform projecting inverse quantum Poisson transform for boundary conditions, which actually given additional linear equations as this form. It sounds much complicated than the previous one, just because boundary condition is much complicated. Then we just need to sum up the previous two linear systems to obtain this kind of linear system L times S is equal to B. The measure L can be written as this form, the equation 28. So you can see it's not a diagonal upper triangular matrix, but still we can observe it still has some sparsity in this matrix. And it can be proved that it's a full-range matrix, and the transition number can be bounded by some parameters. In our paper, we have carefully discussed the tensor encoding of these equations in the general cases. So what's the S and what's the B in here? It's like this. S is as usual. S is all the unknown coefficients from C00 to C33. And the right-hand side, the input function B is a combination with F and G. F is Chebyshev coefficients of the homogeneous F, and G's are the coefficients of boundary conditions of 4 lines. So the state preparation have been discussed in our paper, and after we have solved the S, which means have solved all the CKK in these vectors and by high precision quantum linear system algorithms. And then finally, we need to perform a quantum Poisson transform to transform all the coefficients back to the solution over the interpolation nodes. So yes, that's all. And here I just try to simply to use this sample to show how to construct a simple example 2D Poisson equations by the spectral method. The true case is much complicated. And so first we can briefly give a simple summary of that. And we have already successfully developed quantum algorithms for linear elliptic PDEs based on 2 kinds of algorithms. One is adaptive finite difference methods, and the other is spectral methods. For both algorithms, we successfully achieve complexity, poly dependence of a dimension, and polylog dependence of one of its own. So they are state-of-the-art results for quantum algorithms for elliptic PDEs. And we can consider some future directions as follows. One thing is in the theoretical side, it's natural to consider some extension of these rules. We will be interested to consider how to efficiently simulate some nonlinear differential equations. Actually, several weeks ago, I have proposed one fresh papers for solving nonlinear differential equations recently, but we are definitely interested in continuing this work in future. And we can study some stochastic differential equations, and certainly for concrete applications, we are interested in some applications arising in fluid dynamics and plasma dynamics, and we are interested in applying these results to quantum physics and quantum chemistry. Also, we are interested in some high-dimensional finance models arising in option pricing or other difficult problems. Of course, for PDEs, and we can study the PDE problem in different perspectives. Like we can consider for near-term device, we can consider how to estimate the cost and how to implement the near-term algorithms for that. And also for problem models, we can consider to solve inverse problems. Like given some sample of the solutions, how to estimate an unknown PDEs with some unknown or random coefficients. We can also do these directions with applications in the uncertainty quantifications. Also, finally, we are interested in solving some optimal control and optimal transport problems. We can consider how to combine the quantum algorithms for differential equations with quantum optimizations and quantum machine learning. They are all pretty interesting. So that's all, and just any questions and comments are welcome. Thanks very much.
Thank you, Jin-Peng. That was really helpful. Very nice presentation, and some of the work that you have presented here, I just want to point out to the audience. Um, there's actually 2 to 3 papers, if I'm not wrong, that is published by Jin-Peng and his group from University of Maryland. There's a very well-known professor who's the advisor of Jin-Peng, Dr. Andrew Childs. He and Jin-Peng has published some theoretical work on quantum algorithms for nonlinear partial differential equations recently. So yeah, I will share all those information, and you can actually, I will actually share the link of Jinpeng's research page, where I think so all these details would be there, right, Jinpeng? It's in your website. We can see all those papers that were published recently, right, which you talked about. Okay. So, okay, thank you so much for that talk. It was really, really interesting, very relevant work to what we will be discussing in hackathon tomorrow, when we will be releasing that problem statement. So, before talking about the hackathon, there are questions that have been put up by the audience, which I would like to bring to your attention. So, the first question is. Let me see, where's the first question? So the first question is, how can we be able to calculate properties like enthalpy, entropy, latent heat using quantum?
Sorry, could you please say again?
Okay, so the question is, how can you calculate the properties like enthalpy, entropy, latent heat using quantum algorithms?
That's a pretty good question. Actually, we didn't consider those settings. We just consider how to calculate the solution with some settings. But it would be interesting to consider how to calculate other properties. We haven't considered yet.
Okay, I see. So the next question is, can you solve SFFEE for any thermodynamic system using quantum?
Could you please say the letters again? I didn't get it.
SFFEE.
So what's this? I'm not familiar with that.
Yeah, I'm also. Can the person who put up the question, can you clarify? Is there a spelling mistake there? Or I'm not sure if I know about that term.
I'm talking about the steady flow equation, like steady flow equation, like how to solve in quantum, like steady flow equation. What is thermodynamic system?
Okay, okay, thank you.
Okay.
So it's, yeah, if you heard the question.
Yes, thank you, and that's a good questions. And now perhaps I cannot. I don't know what's the behavior, what's the performance of solving this problem, but just I think it will be pretty interesting. Actually, now they are not very because this direction is pretty new. So there are many kinds of settings, and there are many interesting problems and equations haven't been developed yet. So to the best of my knowledge, for these kinds of equation, I know it's pretty interesting and important, but it seems like haven't been done yet. So it will be interesting to explore this direction.
So, Jin-Peng, so the follow-up question on that would be, all the equations that are being considered are transient equations?
Being considered as what?
Like in your papers and in your research group, the equations that you guys are considering, are they time dependent? Like, are they transient?
Yes, we can consider time-dependent equation. We can deal with that.
Okay. Okay. Sounds good.
Yeah.
So, so the same person actually asked, how to implement the algorithm to solve the Clausius-Clapeyron equation if you are given some kind of settings, like conditions, I would say. Is it possible? Anything that you are familiar with?
Sorry, I don't pretty familiar with that. It might be possible. I can only say that. That's why PDEs are important and hard, and there are many kinds of different settings, and we don't know the answer, but it deserves to try.
Okay, sounds good. Sorry. Okay. So let me see. So on slide 21, is the fourth order boundary scheme necessary for stability of the method?
Slides 21, do you mean the 21 pages? Like this?
Yes, slide 21. Is the fourth order boundary scheme necessary for stability of the method?
No, not yet. We just try to use that as an example. You can use second order or you can use high order. Just it depends on what's your condition.
Okay.
Yeah.
Okay, are there any studies on quantum algorithms for mesh-free methods like particle-based methods?
That's a pretty good question because it seems like they haven't been studied for mesh-free methods. It would be pretty interesting to consider what happened in that.
Yeah.
Yeah, I know, like particle in cells methods, and they're pretty interesting in the study of plasmas and fluid dynamics, but it seems like haven't been considered yet.
Yeah, because I think so the particle-based methods are seeing very like lot of interest, and it would be great to actually see in quantum. And I think so you pointed out that, right, that the field is relatively very new. So these methods and algorithms are just starting to come up. I think so when I was looking into like solving PDE using quantum algorithms, there were very less number of groups who are actually doing that, and Jin-Peng's group is one of those methods, like one of those groups who are doing this method. So Another question is, how can we use quantum algorithms for finite element methods?
Yes, we can use. Actually, there are one paper to use finite element method for that. Perhaps let's just let me try to find it. Like one paper is here is finite element method for Maxwell equation. There is one paper here, but in my to the best of my knowledge, there haven't been extended study for this approach. I think it can be generalized to many kinds of problems by finite element methods. Yes.
Okay, so a follow-up question that I would have on that is, these are theoretical calculations, right? They have not been practically implemented.
Mm. It depends, and for this line, if we try to consider like the quantum linear system algorithm by HHL settings, it's pretty hard to be implemented. I know perhaps some groups are trying to input some towing model, for example, there are some people only try to implement very low dimension, like 4x4 system, only 4x4 system solving by HHL. So we can only implement some pretty small scale by lab, but it's not a main line of the development of labs. In another case, as I mentioned before, for heuristic studies, and there are a few people try to use different approaches to attack them, but perhaps they are not pretty suitable to solve PDEs.
I see. Okay, great. So the next question is, the method described. Okay, I think so. That was the same question that I just asked. So, okay, so I think so. The follow-up question, the person put up the same question that I asked and had a follow-up question also, that because we have like limited number of qubits, can these be practically implemented in actual quantum computers right now or not?
Yes, I agree. Yeah.
Okay. Yeah. So the next question is, can we simulate thermodynamic systems like open or closed systems using Hamiltonian simulations?
That's a good question. General, it might be possible, but I haven't seen very concrete setting in this field. Perhaps when we consider open or closed system directly simulated by Hamiltonian simulations, that basically care about how to efficiently simulate Schrödinger equation, how to, for example, find ground state energies of Schrödinger equation of a quantum manifold system. So if we talk about what's the thermodynamics, sometimes people refer to some quantum settings of the thermodynamics. But for the classical thermodynamics, it might be hard to directly simulate by Hamiltonian simulations. So it's not very relevant to you. Or you can say that the current study directly using Hamiltonian simulations not pretty close to the thermodynamics we care about in the PDE settings.
Okay, great. So another question is, can quantum algorithm be used in BMI?
So sorry, what's the BMI?
I think so. It's something related to civil engineering or architecture. Can person who asked this question clarify? Maybe you can just write it in chat. Okay, while we wait for the person to give the clarification on what's BMI, the next question is, which is the top journal which publishes work on quantum algorithms applied to computational science? JCP, or is there specific, or is there something specific, more specific?
Yeah, good questions. And I have one paper published in CMP, Communications in Mathematical Physics. So basically, we can find some mathematical physics journal to publish, like I have a CMP. Also, some people publish in JMP or other like the PRA, or of course PRL is good, and some physical journals, PR series. And the JCP is possible perhaps, but I didn't submit our group's papers to that. I don't know if other guys do that, but I haven't seen it yet.
Okay, so just for the audience, so that everybody is on the same page, can you um, spell those out, like the ones that you mentioned would be relevant? I think so that will be very helpful for the audience. I mean, you can put it in chat if you want. Um, Maybe after the last question that we have is
I would like to ask a question about this. What are the restrictions in using quantum algorithm to solve complex multi-physics equations like computational fluid dynamics, and what accuracy can we expect in solving these equations? How much accuracy?
Okay, thank you for that. Jin-Peng, did you get that, or should I repeat the question?
So can you repeat again?
Yeah, so the person asked basically that what are the challenges that entails when you have complex computational or multiphysics simulations, um, like like a computational fluid dynamics, in like quantum algorithms, and when you implement it in actual quantum computers, what's the challenge currently?
Yes, there are a few challenges, and I think all the classical challenges will directly bring into the quantum challenges, and also quantum has its own challenges. But of course, perhaps some classical challenges are not very hard in the quantum side. For example, we can speed up the dimension. But for fluid dynamics, it's a low-dimensional example. So basically, I think the hard problem in fluid dynamics are still hard in quantum computers, like the nonlinearities, like we have the turbulence, the subwaves, and many other properties. And now, currently, in my understanding, they are still hard to be simulated in quantum computers. Then quantum computers will have their own challenges, like implement the proper algorithm will be limited by by the number of qubits, like limited by our current ability to build quantum computers, and also be limited by some properties from quantum mechanics. So like some PDEs maybe we cannot efficiently simulate, and it depends on how to design a quantum algorithms. Also depends on the property of PDE itself. So they will sometimes I can only say they should be case by case and discussed.
Hi sir, is the quantum computer 100% accurate? Means the result obtained from quantum computers right now?
So Jin-Peng, the question is, are the quantum computers accurate, like the current generation? I mean, the straight answer is no, but if you can give your input on that, that would be great.
I think yes.
So, I mean, isn't the problem of like error that exists in current generation of quantum computer there?
Sorry.
So in the current generation of like quantum computers, there is this error or like noise that we say that exists. So doesn't that isn't that a challenge in the current generation of quantum computers?
Yes, that will be a large challenge for that. And now for the development of our side, we didn't deal with this decoherence and deal with some about how to consider the faults in that. And we just consider how to develop basic quantum algorithms, assume that we have a very powerful fault tolerance quantum computers, and we can guarantee that the calculation is correct like this. So I know that in the engineering part, it will be very large challenge in that.
Okay, thank you. So the last question that we had, which we needed some clarification, was the BMI. So BMI stands for brain-machine interface. So can quantum algorithm be used for brain-machine interface?
Perhaps I didn't consider yet, but it sounds pretty interesting. Yeah.
Okay, great.
I have a follow-up question, if you don't mind.
Yeah, sure. Go ahead, please.
Great presentation, Jin-Peng. Loved it. I have a question about your algorithms which you implement. So I've looked at your archive paper. So you give an example for solving a two-dimensional Poisson equation using your algorithms. So have they been implemented, say, in an emulator case, or it's just purely theoretical right now? Because it would be great look at some results if they've been actually implemented on an emulator.
So I think so. So Jin-Peng, if you want me to repeat the question, it's basically the Poisson equation that has been implemented in one of your papers has that been implemented in an emulator, which I think so. The answer is no, because those are theoretical results. But I can be wrong. Please, Jin-Peng, if you can.
You're correct. I agree. Yeah.
Okay, so it's theoretical, I think. Okay, so yeah, so just to follow up on Rohit, so we have been looking into the papers that are coming out from Jin-Peng's group. We are quite interested in that, and I can say that it's actually the work is very innovative in the sense that I think so it is one of those papers that, like, few of those papers which really implements or tells the algorithm which needs to be implemented for these solving these PDE, but because the math is really challenging and the quantum, it's not really easy to like convert that into a quantum algorithm that can be implemented in like emulator. But there might be people who might be trying that. Haven't seen any literature on that yet. So I think so this will be the last question. And Ruth, if I know you mentioned that YouTube doesn't have any questions, so if not, then this would be the last question. Is there one introductory paper that you would recommend for anyone who is starting off in this field, given that the person has a significant experience in developing traditional numerical methods? So the person is comfortable with math, but is there any introductory paper that the person can start on the quantum side of things?
That's a good question. I think perhaps you can start with my advice, Andrew Charles lecture notes. This lecture notes is very famous in our field, and I think it's a good starting point of all the people studying quantum algorithms. Just call Andrew Charles lecture notes.
Okay, so yeah, thank you. So basically, I can just type out the name here. Dr. Andrew Childs.
Yeah, I think you can easily find this lecture notes in my advisor Andrew's website.
Yeah. Okay, great. I think so we are through with all the questions. Thank you everyone for joining, and I would like to take a minute to thank Jin-Peng for this amazing lecture that you have put up. Thank you so much for your time and effort that you have spent on preparing this lecture. It was really helpful, and I think so it was very helpful for the audience as we kick off our hackathon tomorrow. So going on to those details now for people, because I know many people are waiting for more information on the hackathon. So what is going to happen is today we are going to compile all the list of people who have attended today's